These are the newest calculations about 3I Atlas, and they reveal something that should not be possible. On March 16, 2026, this interstellar visitor will pass Jupiter at a distance of exactly 33.21 million miles. And here's why that number is so disturbing. Jupiter's Hill radius, the gravitational boundary where Jupiter's gravity overcomes the Sun's influence, is 33.24 million miles. The difference? Only 35,000 miles. That's a margin of error of 0.1% across a distance of 33 million miles. The statistical probability of this happening by chance is approximately 1 in 26,000. So in this video, I'll break down what is actually happening with 3I Atlas and Jupiter, because the math behind this encounter suggests something far stranger than a random flyby. Let's start with where we are right now. As of late November 2025, 3I Atlas has passed through perihelion and is moving away from the Sun. It survived the closest approach to the Sun on October 29th without fragmenting, which was already surprising given the massive jets it was producing. Now the object is cooling down, getting fainter and heading toward its next major gravitational encounter. On March 16, 2026, less than 4 months from now, 3I Atlas will make its closest approach to Jupiter. This isn't just another planetary flyby, this is a precisely calculated encounter at a gravitationally significant boundary. Data has been flooding into NASA's Jet Propulsion Laboratory from more than 230 observatories across the globe, forming a comprehensive observational network dedicated to tracking the incoming object. These measurements have allowed scientists to calculate the object's expected distance from Jupiter at closest approach with extraordinary precision. And what those calculations reveal is something that challenges our understanding of how natural objects move through space. To understand what's happening, we need to talk about the Hill radius. This is not just a theoretical concept, it's a real, calculable boundary around every planet, where that planet's gravity becomes dominant over the Sun's gravity. Inside the Hill radius, a planet can capture objects, pull them into orbit, or at least significantly alter their trajectories. Outside the Hill radius, the Sun's gravitational influence is too strong, and the planet cannot hold on to anything. The Hill radius is calculated using exact physical parameters. The mass of Jupiter, which is about 318 times the mass of Earth, the mass of the Sun, which is about 1,047 times the mass of Jupiter, and the distance between Jupiter and the Sun, which varies as Jupiter orbits but averages about 5.2 astronomical units. For Jupiter on March 16, 2026, taking into account its exact position in its orbit, the Hill radius calculates to approximately 33.24 million miles, or about 53.5 million kilometers. This is the invisible sphere around Jupiter, where its gravity rules. Now, the most recent trajectory calculations for 3I Atlas place its closest approach at approximately 33.21 million miles. The object will pass just inside Jupiter's Hill radius by a margin of only 35,000 miles. Let's put this precision into perspective. Imagine you're trying to throw a dart at a target 33 million miles away, and you need to hit within 35,000 miles of the bullseye. That's hitting a target with 0.1% accuracy across an astronomical distance. Even our most sophisticated spacecraft missions, planned by teams of engineers with supercomputers and decades of experience, struggle to achieve this kind of precision on the first attempt. When we send probes to other planets, we typically need multiple course corrections along the way to hit our target. The Mars rovers, for example, required several trajectory correction maneuvers during their journey to Mars. The New Horizons mission to Pluto needed multiple course adjustments to hit its flyby target. Even with active guidance and propulsion, hitting a precise target in space is extremely difficult. Yet 3I Atlas, supposedly a natural object with no propulsion system, no guidance computer, and no mission control, is on track to hit Jupiter's Hill radius with precision that would be impressive even for an engineered spacecraft. Calculations suggest the probability of this happening by pure chance is roughly 0.004%. That's one chance in 26,000. To put it another way, if you observe 26,000 random interstellar objects passing through the solar system, you would expect only one of them to pass this close to Jupiter's Hill radius by coincidence. But here's where it gets even stranger. 3i Atlas didn't start out on this trajectory. The object has undergone measurable non-gravitational acceleration during its journey through the inner solar system. Observers tracking the object noted that its trajectory was deviating from the path predicted purely by gravitational interactions. These deviations were quantified as an acceleration of approximately 5 times 10 to the negative 7th astronomical units per day squared. This acceleration shifted the object's trajectory by approximately 62,000 miles, and that shift was in exactly the right direction and exactly the right magnitude to bring the object from wherever it would have gone naturally to a point precisely at Jupiter's Hill radius. Think about what this means. The object entered the solar system on one trajectory. Non-gravitational forces, whether from outgassing, solar radiation pressure, or something else, altered that trajectory, and the alteration was precisely calibrated to place the object at this gravitationally significant boundary. For natural outgassing to produce this result would require an extraordinary coincidence. Outgassing is chaotic and unpredictable. Jets fire in different directions as the comet rotates. The net effect on the trajectory is usually small and somewhat random. For outgassing to produce a 62,000-mile course correction in exactly the right direction to hit the Hill radius within 35,000 miles is like throwing a dart blindfolded and hitting the bullseye. So why does the Hill radius matter? What's special about this particular distance? The Hill radius represents a gravitational sweet spot. Inside this boundary, Jupiter's gravity is strong enough to capture objects and hold them in stable orbits. But there's more to it than just capture. At the Hill radius, you also find the Lagrange points, special locations where the gravitational forces of Jupiter and the Sun balance perfectly. These are the most stable locations in the Jupiter system for placing objects that need to remain in position with minimal fuel expenditure. The James Webb Space Telescope, for example, sits at a Lagrange point in the Earth-Sun system. It's a stable location that requires very little fuel to maintain. Around Jupiter, the Lagrange points near the Hill radius would serve the same function. If you wanted to place a probe in the Jupiter system with minimal energy expenditure, you would aim for the Hill radius. If you wanted to deploy multiple smaller probes that would remain in stable orbits around Jupiter, you would release them at the Hill radius. And if you were an interstellar probe designed to study the Jupiter system, arriving at the Hill radius would be the optimal strategy. You could release subprobes that would remain in stable orbits, studying Jupiter and its moons for extended periods, while the main craft continues on its journey. This is exactly what Avi Loeb has suggested might be happening with 3i Atlas. We have one spacecraft currently in the Jupiter system that could observe 3i Atlas during the encounter, the Juno probe. Juno has been orbiting Jupiter since 2016, studying the planet's atmosphere, magnetic field, and interior structure. During the March 2026 encounter, Juno will be in a unique position to observe 3i Atlas from a vantage point we cannot achieve from Earth. The distance between Juno and 3i Atlas at closest approach will be approximately 0.4 astronomical units, or about 60 million kilometers. That might sound far, but it's actually quite close in astronomical terms. Juno's cameras and instruments could potentially capture detailed images and data about 3i Atlas that would be impossible to obtain from Earth-based telescopes. Researchers have calculated the optimal observation window, taking the maximum distance from Juno to be 0.4 AU for optimal observation, and considering when the distance between 3i Atlas and Juno is less than the distance between 3i Atlas and Jupiter itself, the optimal period for observation is from March 9th to March 22nd, 2026. This 2-week window is critical. If anything unusual is going to happen, a course change, a deployment of sub-probes, an unexpected burst of activity, this is when we would see it, and Juno would have the best seat in the house. What will actually happen when 3i Atlas passes through Jupiter's Hill radius? Even if the object doesn't release any probes or perform any maneuvers, Jupiter's gravity will have a significant effect on its trajectory. This is called a gravitational slingshot or gravity assist. As 3i Atlas approaches Jupiter, the planet's gravity will pull on it, changing its velocity and direction. Depending on the exact geometry of the encounter, Jupiter could speed up the object, slow it down, or deflect it in a new direction. We use this technique routinely for spacecraft missions. The Voyager probes used gravity assists from Jupiter and Saturn to reach the outer solar system. The Cassini mission used multiple gravity assists to reach Saturn. It's a way to change a spacecraft's trajectory without using fuel. For 3I Atlas, the Jupiter encounter will determine its final trajectory out of the solar system. The object is currently moving at about 58 kilometers per second. After the Jupiter flyby, that velocity could change by several kilometers per second, and the direction could shift by several degrees. These changes will determine where 3I Atlas goes next. Will it be deflected toward the outer planets? Will it be sent on a trajectory that takes it out of the solar system faster? Or will something unexpected happen that changes the trajectory in ways we can't predict? There's another important aspect of the Hill radius that Avi Loeb has emphasized. At this precise distance, Jupiter's gravity is strong enough to overcome the Sun's tidal forces. Tidal forces are the differential gravitational pull across an object. When an object is near a massive body like the Sun, the side closer to the Sun experiences stronger gravity than the side farther away. This difference can stretch and tear objects apart. Inside Jupiter's Hill radius, Jupiter's gravity is strong enough to hold objects together against the Sun's tidal forces. This means that if 3I Atlas were to release smaller probes at this location, those probes would remain intact and could be captured into stable orbits around Jupiter. Outside the Hill radius, the Sun's tidal forces would be too strong. Any released probes would be pulled apart or scattered. They couldn't remain in stable orbits around Jupiter, so the Hill radius isn't just about gravitational capture, it's about the stability of released objects. And 3I Atlas is arriving at exactly the distance where released objects would be stable. As Loeb puts it, it arrives just at the right distance, so that Jupiter's gravity will overcome the Sun's tidal gravity, and anything it releases, there will stay there, which suggests why did it arrive exactly at that distance in order perhaps to release some probes near that planet. Of course, not everyone agrees with the technological interpretation. Let's examine the alternative explanations that have been proposed by other researchers. Explanation 1. Trajectory calculation errors. Even with data from 230 observatories, there are still uncertainties in the trajectory calculations. Small errors in measuring the object's position and velocity can accumulate over time, leading to errors in predicting future positions. If the current trajectory calculations are off by even a small amount, the predicted closest approach distance could change. Maybe 3I Atlas won't actually pass as close to the Hill radius as we think. Refining the calculations over the next few months will help resolve this uncertainty. Explanation 2. Exotic cometary outgassing. Some researchers have suggested that 3I Atlas might have unusual outgassing properties that produce more consistent and directional thrust than typical comets. If the object has a very uniform distribution of volatile materials, or if its internal structure channels gases in specific directions, the outgassing could produce a more controlled trajectory change. This would still be a natural process, just one we haven't observed before. It would expand our understanding of cometary physics without requiring any artificial explanation. Explanation 3. Pure statistical coincidence. Over the billions of years that the solar system has existed, countless interstellar objects have likely passed through. We've only detected 3 of them because our detection capabilities are limited. With enough objects passing through over enough time, eventually one would hit this kind of statistical outlier. It's like the lottery argument. The odds of any individual winning are tiny, but someone eventually wins because so many people play. Maybe 3I Atlas is just the lucky winner of the cosmic lottery. But here's the problem with dismissing the Jupiter encounter as coincidence. It's not the only anomaly. 3I Atlas has displayed a consistent pattern of unusual behaviors that, taken together, are difficult to explain with natural processes alone. The object has a retrograde trajectory perfectly aligned with the ecliptic plane, statistically unusual for interstellar objects. It has jets pointing toward the Sun, defying normal cometary physics. It has a perpendicular jet confirmed by the Mars Reconnaissance Orbiter that cannot be explained by any known natural mechanism. It has unusually high nickel content and almost no water. It has extreme negative optical polarization never seen before in any natural object. It has non-gravitational acceleration, suggesting massive mass loss without a visible debris cloud. It has collimated jets that maintain orientation despite rotation. It survived perihelion intact when it should have fragmented. It displays rapid color changes and a green glow that appears and disappears. And observers report visible rotation changes within minutes that don't match the measured 16-hour rotation period. Now add the Jupiter encounter at precisely the Hill radius. Each anomaly on its own might be explainable as an outlier or a measurement error, but together they form a pattern. And that pattern is what makes researchers like Avi Loeb take the technological hypothesis seriously. So what should we be watching for during the March 2026 encounter? If 3I Atlas is a natural object, we would expect to see predictable gravitational effects. The trajectory should bend according to Jupiter's gravity. The object might show increased activity due to tidal stresses, but nothing fundamentally surprising should happen. If 3I Atlas is an exotic natural object with unusual properties, we might see unexpected responses to Jupiter's gravitational or electromagnetic environment. Maybe the jets change in intensity or direction. Maybe the rotation rate changes. Maybe we detect new emissions or signatures we haven't seen before. But if 3I Atlas is artificial, if it's a probe designed to study the Jupiter system, we would expect to see deliberate actions. A course correction to adjust the flyby distance, a change in rotation rate or orientation, the deployment of smaller objects that remain in Jupiter's vicinity, or some kind of signal or transmission. The key indicators would be changes in trajectory that cannot be explained by gravity alone, the appearance of new objects near Jupiter after the encounter, unusual emissions or signals during the flyby window, or changes in the object's rotation, brightness, or spectral signature that suggest active systems. Any of these would be strong evidence that 3I Atlas is not what it appears to be. After the Jupiter encounter, 3I Atlas will continue its journey out of the solar system. Based on current calculations, the object will be headed toward the Gemini constellation with a velocity of approximately 58.01 kilometers per second. This is slightly faster than its incoming velocity from Sagittarius, which was about 57.9995 kilometers per second. The small increase is due to gravitational interactions with the Sun and planets during its passage through the inner solar system. At this velocity, 3I Atlas will cross Neptune's orbit within a few years. It will pass through the Kuiper Belt, the region of icy bodies beyond Neptune, and eventually it will cross the heliopause, the boundary where the Sun's influence ends and interstellar space begins. That journey will take decades. By the time 3I Atlas reaches the heliopause, it will be too faint for even our most powerful telescopes to detect. We will lose track of it, and unless we send a probe to follow it, we will never know what happens to it after it leaves our solar system. This makes the March 2026 encounter even more critical. It's our last chance to study this object in detail. It's our last chance to determine whether it's natural or artificial. After Jupiter, 3I Atlas will fade into the darkness, taking its secrets with it. So what should humanity be doing right now? First, we need to maximize observations between now and March 2026. Every telescope that can point at 3I Atlas should be doing so. We need continuous monitoring to refine the trajectory and watch for any changes in behavior. Second, we need to coordinate a global observation campaign for the Jupiter encounter. Multiple telescopes, multiple wavelengths, continuous coverage. We cannot afford to miss anything that happens during that critical 2-week window from March 9th to March 22nd. Third, we need to task the Juno spacecraft to observe 3I Atlas if technically feasible. Juno has the best vantage point for the encounter. Even if it means interrupting its primary mission for a few days, the potential scientific return is enormous. Fourth, we need to prepare for rapid response. If something unusual happens during the encounter, we need to be ready to follow up immediately with additional observations and analysis. We need teams on standby ready to interpret data in real time. And fifth, we should seriously consider a probe mission. If we act quickly, we might still be able to launch a spacecraft that could catch up to 3I Atlas after the Jupiter encounter. We have the technology. We've done it before with comets. The question is whether we have the will and the funding to do it now. Folks, what is actually happening with 3I Atlas and Jupiter is this. An interstellar object that has displayed 12 separate anomalies inconsistent with natural comets is now on a trajectory that will bring it to Jupiter's Hill radius with 0.1% precision. The probability of this happening by chance is 1 in 26,000. The object underwent a 62,000-mile course correction that was exactly the right magnitude and direction to place it at this gravitationally significant boundary. And it will arrive at the optimal location for deploying probes that would remain in stable orbits around Jupiter. This could be the most important astronomical event of our generation. On March 16, 2026, we will learn whether 3I Atlas is an exotic comet, a natural plasma phenomenon, or an artificial probe sent by another civilization to explore our solar system. We have less than 4 months to prepare. 4 months to coordinate observations, 4 months to make sure we don't miss what could be the most significant discovery in human history. If you watch to the end, drop me a like and subscribe for more updates. And click on the video appearing on your screen right now, where we break down all 12 anomalies of 3I Atlas and explain why each one challenges our understanding of natural objects. I'll see you in the next one.